Let's talk about the organic acids section of the test. You see it here on the right. Organic acids are produced through metabolic functions. So remember, organic acids aren't really nutrients. They're metabolic byproducts. Nutrients like amino acids, lignans, flavonoids go down pathways. They're metabolized. And organic acids are metabolic byproducts of those nutrients. They're measured on the NutrEval by first morning void urinalysis. Always urine first morning void on organic acids. And they're categorized into groups based on their clinical relevance. So you see here, for example, malabsorption, dysbiosis, yeast fungal dysbiosis as categories in terms of clinical relevance. The markers are ratioed to the creatinine concentration. That's really important. Creatinine concentration gives us some insight into renal function, but since all of the markers on this page are ratioed to creatinine, we want to have a good level of creatinine so we know we have a good specimen. If we have an extreme low or extreme high of creatinine, that can really influence the findings. So let's look at one of these sections. In fact, we'll look at all of them individually. First, let's look at the malabsorption and dysbiosis markers. Now, if you have a patient with gut issues, this is an interesting point of view of gut function. But the gold standard would be a GI-FX stool 2200 in order to get a really closer look at gut function. But here we can look at malabsorption and dysbiosis markers. You see, for example, an elevation of the 3-hydroxyphenylacetic acid and the benzoic acid. So with the 3-hydroxyphenylacetic acid, for example, we know that there are various nutrients that are related to this particular organic acid. Things like wine and grapes and cranberries and black tea and orange juice, grapeseed extract. These are nutrients that can be converted in the gut by anaerobic bacteria into 3-hydroxyphenylacetic acid. And when that occurs, we're seeing a very high concentration. We may wonder about an imbalance amongst the various bacteria that are making the conversion, thus dysbiosis. It could also reflect some degree of malabsorption, because if we're taking in, for example, proteins and other nutrients and they're not readily absorbed in the small gut and they linger, that provides more opportunity for those anaerobes to convert the nutrients into this organic acid. The same holds true with benzoic acid as well. So these elevations can lead us in the direction of malabsorption and dysbiosis. Benzoic acid, by the way, is very commonly elevated because it's a very common preservative. If you look at any canned or bottled beverage, you're likely to see sodium benzoate or potassium benzoate as a preservative. Let's look at the cellular energy and mitochondrial metabolites. And I touched on these earlier with the Krebs cycle. So we have carbohydrate metabolism, energy metabolism, fatty acid metabolism, all the various organic acids involved in the Krebs cycle and the production of energy in the mitochondria. So for the Krebs cycle, when we look at these organic acids, just be aware this is not a substitute for a muscle biopsy for mitochondrial function. What we're doing is we're looking at the organic acids in the context of the pathway chart of the Krebs cycle to see if there are any obvious imbalances. And when we see those imbalances, we think about the specific nutrient cofactor support that we could provide. Let's take a look at the cellular energy and mitochondrial metabolites next to the Krebs cycle at a glance pathway chart that we provide on the test. Again, we know that the idea of the Krebs cycle is to take macronutrients, fats as fatty acids oxidizing, carbohydrates through glycolysis making pyruvic acid and lactic acid, proteins as amino acids making acetyl-CoA, and that those macronutrients provide us with acetyl-CoA, and that the acetyl-CoA is going to fuel in the mitochondria the citric acid cycle. So if we're looking at carbohydrates as they produce pyruvic acid and lactic acid, that looks just fine. But then the pyruvic acid has to make acetyl-CoA. what nutrient cofactors are required for that pathway? Well, everything in the green circle indicates that we're looking at nutrient cofactors that must be there adequately to move the pathway ahead. So for pyruvic acid to convert to acetyl-CoA, we need adequate magnesium, lipoate, B1, 2, and 3. So this is a way that we can look at imbalances. If we had seen an elevation of pyruvic acid, we'd wonder, why is that high? Well, it may be that it would be having difficulty in its conversion to acetyl-CoA. What would we consider necessary? Magnesium, lipoate, B1, 2, and 3. Those would be the cofactors. Now bear in mind that there is also the possibility that various toxics can block the pathway. So if pyruvic acid had been elevated, and I know it's not here, but if it had been, it may also be that it's arsenic, mercury, and antimony that are elevated, creating a blockage. More typically with toxics blocking a Krebs cycle function, you'll see a more global shift to the right. Let's now look at a second section here, the metabolic analysis markers for neurotransmitter metabolites. Now remember, with the neurotransmitter metabolites, we're tracking metabolites from various neurotransmitter pathways. But these metabolites do not provide direct measurement of dopamine or serotonin or epinephrine. The status of the metabolites can provide data regarding nutrient cofactor needs. So we're not looking at dopamine directly, but we're looking at the pathway, very much like we just did with the Krebs cycle. When I'm doing consults on the phone for this, often I have doctors asking me, what are those various pathways? Do you have a chart? Well, I've heard you out there asking, and so I did create this catecholamine metabolism chart on the right. So on the left, we're looking at the neurotransmitter metabolites. We measure homovinylic acid, and we measure vinylmandelic, as well as 3-methyl-4-hydroxyphenylglycol. So if you look at these various markers on this chart, tyrosine is an amino acid. It converts into dopamine. Dopamine gives us a sense of focus, focus and well-being. So dopamine converts into the homovinylic acid that we look at on the left. At 3.7, it looks fine. But dopamine also converts into norepinephrine, epinephrine, adrenaline, normetanephrine, and then finally the 3-methyl-4-hydroxyphenylglycol and the vinylmandelic acid. By tracking these imbalances, we can get a sense of what might be going on, what kind of nutrient cofactors may be needed to better balance the pathway. The same thing holds true for serotonin metabolism. Again, at your request, I have put together this pathway chart whereby tryptophan, the amino acid, converts, into 5-hydroxytryptophan, which we often provide for our patients to help them sleep. Now, 5-hydroxytryptophan makes serotonin. We often think of serotonin in the brain, but the vast majority of serotonin is in the gut. Serotonin will be methylated to make melatonin. Melatonin helps us with our circadian rhythms, but is also an antioxidant and anti-inflammatory. Serotonin then makes 5-hydroxyindoleacetic acid. In this case, we have an elevation. So there are a few possibilities to consider. If the patient is supplementing tryptophan or 5-hydroxytryptophan, we may expect to see an elevation. If there are SSRIs, we may expect that. But if there are gut issues, if they're burning through a lot of serotonin under stress, these are the kinds of discussions we can have in analyzing the neurotransmitter metabolites. Understanding the pathways is really key for that. Organic acids provide us with great insight into functional need for vitamins. You can see this vitamin marker section with a listing of various organic acids. When we look at this, we can see there's, for example, an elevation of methylmalonic acid. So how does that elevation of methylmalonic acid provide insight into a specific vitamin need? Let's take a look at the various vitamin markers in terms of organic acids and how they work. You see the methylmalonic acid somewhat elevated. So you have this organic acid. The breakdown of that organic acid requires specific vitamin and mineral cofactors. The elevation of an organic acid may indicate a functional need for specific cofactor supplementation. In other words, methylmalonic acid needs a specific vitamin and or mineral cofactor, in this case B12, in order to be broken down. So if that B12 functionally isn't doing the job, you'll see an increase in the level of methylmalonic acid in the blood, which means it'll get dumped into the urine in higher concentrations. So as we see here, we have a higher level of methylmalonic acid. When we look at specific elevations of organic acids, they provide insight into what specific nutrient cofactor may be required. Methylmalonic acid conversion requires vitamin B12. Elevated levels of methylmalonic acid in the urine and urinary excretion tells us that we need more B12 functionally to better break methylmalonic acid down. Our section on toxin and detoxification markers includes alpha-ketophenylacetic acid, which reveals an exposure to styrene, styrofoam, plastics, exhaust fumes. Alpha-hydroxyisobutyric acid reveals exposure to MTBE, which is a gasoline additive that was used to lower gasoline emissions in the 1990s through the early 2000s. Pyroglutamic acid is both a precursor and breakdown product of glutathione, an important antioxidant and detoxifier. Our key points for organic acids. Organic acids are produced through metabolic functions. They're measured through first morning void urinalysis. Organic acids are categorized into groups based on their clinical relevance. Thanks for listening. I'm Stephen Goldman, a medical education specialist at Genova, and I'll see you on the phone.